Hi, good morning, everyone. So I'm going to be giving a quick introduction to Quantemol-EC. I'm going to be very briefly presenting some work which one of our scientists has done. And then finally, I'm going to be giving a quick demonstration of the product. So first up, an introduction to Quantemol-EC. So Quantemol-EC is a piece of software for calculating electron molecule scattering cross-sections and other similar observables. It's based off a newer suite of R matrix codes, and it interfaces with both MolPro and UKR Mol Plus to generate the most accurate recent cross sections. So some of you may be familiar with our Quantemol-N software, which is the software which preceded Quantemol-EC, which did a similar thing. So some advantages which Quantemol-EC has over Quantemol-N. It allows for the automatic generation of configurations, symmetry detection, and for the automatic handling of degenerate states. Now, this is very useful for a newer user who's not super familiar with the underlying science potentially, because it makes everything a lot more automated and a lot more simple. It also provides more accurate ionization cross-section calculations, which are very useful for multiple fields. And it has access to the most recent version of the R matrix codes. So Quantemol 1.2 is the newest version, which we released last year. So some new features which came along with that. So it can calculate non-resonant vibrational excitations for ions and neutral species. It can utilize effective core potentials for ionization cross-sections, which is really useful for larger atoms so that you don't have to calculate your core electrons. And yeah, can save time and get very accurate results. And free trials are available now. So if that's of interest to you, then please email us at sales@quantemol.com. But you'll probably hear that a number of times during today. So now I'm going to be very quickly taking you through a piece of recent science which my colleague Harren did. Now, I warn you, Harren is a scientific expert along with Jonathan. I'm very much sales and marketing, so I'm going to be doing my best to explain this. But if you have any more in-depth questions, then potentially we could pass them on to Jonathan, or you can put them in the chat and I will make sure Harren gets back to you with them. So quick motivations. So why do we want to study this? Why do we want to do these calculations? So C4F8 is used in space and heavily in space and nanotechnologies. So those are fairly big applications for it. But why do we want to do the calculations? Well, there's no data available for complex targets. There's no molecular process. Not all the molecular processes have data. So certain breakdown routes didn't have data. And finally, we wanted to use the numerical data in order to fuel plasma simulations. So just very quickly, some of the molecular processes which are at play in this process. Some of these will be results for some of these will be presented a little bit later on in this presentation. Low impact energies, we have elastic scattering and momentum transfer. We also had a look at rotational and vibrational excitation. We had a look at electron impact, electronic excitation and de-excitation. We had a look at electron impact dissociation, electron impact ionization, dissociative ionization, and dissociative electron attachment. And you can see on the right, we have the optimized geometry of the molecule and its symmetry group. So very quickly, going on to the first one of those, the elastic and momentum transfer cross sections were calculated. And here you can see they're compared with literature. And you can see that the general trends which have been calculated are quite accurate to literature. So you can see for the elastic scattering, it returns to a similar level. The shape of the things of the cross section seems to come down quite nicely with the onset shown. in the work by Winstead and McCoy. And then if you look at the momentum transfer cross section, you can see that again it follows a fairly similar trend as the work presented here. So on top of that, we did electron excitation cross sections. So I had a quick look at these. So this is for 4 given states. So these are very, very useful and have lots of applications, as I said, within space and nanotechnology. And you can see that those have all been calculated. And from the accuracy of the previous one, we draw confidence that these are also fairly accurate. Again, we've got some vibrational excitations, which are presented here. Here we've predicted 6 of them. And you can see some fairly useful features, which can be used for a multitude of different applications. So here we've calculated the total and partial ionization. So as you can see from this, we can compare the total ionization as calculated by QEC with an experimental total ionization, and you can see that fits very, very nicely. On top of that, which gives us confidence that the partial ionizations are likely fairly accurate too. Yeah, so just a quick summary of that work before I go on to doing a demonstration of Quantemol-EC. So the work shows the importance of ab initio calculations. As you could see, some of the data which we were calculating wasn't available in previous literature. So this gives us the ability to access that information. You didn't necessarily see this bit, but well, you did see this bit. So you also saw the flexibility of the R matrix method and what sort of problems it could be applied to. It agreed well with experimental data, especially that last ionization calculation. Yep. So this is something which you couldn't see, but I've been informed that QEC is easy to use and accessible to non-experts. Very easy to use during this work. And finally, another thing which I've been informed is the inclusion of more ab initio data into existing data sets can give significant differences. So at this point, I'm going to be doing a quick demonstration of how Quantemol-EC works. Okay, super. So if one were to open up Quantemol-EC, then this it would be your landing spot. So the first thing which one would do to start a new calculation is to click File and then New. So this is an interface which would allows you to build your molecule. So I'm going to quickly build a water molecule, as previously mentioned. So I'm going to click Add Atom, and then say Oxygen, and I'm going to have that at the origin. Click OK. So now maybe I want to add another atom, let's say a hydrogen atom. And I'm going to put this at 0.8 and 0.5. And then I'm going to add a second hydrogen atom. This one is going to be at 0.8 and minus 0.5. And that is a rough approximation of a water molecule. So luckily, it doesn't need to remain rough because we have MolPro tied into this piece of software. So if one were to purchase this software, you'd also need to have access to a MolPro license. The free trials we mentioned earlier, you can also get free trials of MolPro, and we have a link available for that. So yes, you can do a free trial of both, but you would need a MolPro license in order to run the software. So I'm going to click optimize. So you have 2 methods of optimization. You can either optimize through Hartree-Fock theory, or you can utilize density functional theory with a B3-lit functional. If you don't know what that means, don't worry too much about it. Hartree-Fock works absolutely fine for most situations. And you can also control your basis set. For water, this isn't going to make a huge amount of difference, but if you have expertise in basis sets, then feel free to edit it. And you can also tell it what your charge is. So I'm just going to do a quick optimization like that. And when it optimizes, it's going to give me the option to resave my geometry file, which in this case, I'm going to click no. But if you do an optimization, then feel free to save your geometry file. And you can see there's my water molecule, and it has the new atomic coordinates there. It prints out the bond lengths, and it also prints out the bond angles. If you wanted to change it at this stage, you can type things into this and then re-optimize. So the next important step is to click center to put the molecule in the center of the box. And then when you're done with that, you can click next. So yeah, this is another useful piece of technology which one can do. One can now automatically calculate your point group, which is really useful because if you don't have expertise in symmetry sciences, then this really speeds things along. So if you click OK on that, that should be really quick as long as you don't have a really massive molecule. And you can see here it's worked out the symmetry for my water molecule. And at this stage, you then can select a couple more details about the calculation. So first up, you can decide on what orbital type you want to use. Now, this might seem a little bit, I guess, intimidating if it's not something you're particularly used to doing. We've got lots of literature for this. We're always happy to help you if you email us. Generally speaking, using Hartree-Fock orbitals is okay for most systems. And natural orbitals, using multi-configuration or SF, generally speaking, are better for excited state calculations. So in this case, I am going to be using MCSCF because I'd like to be doing some excited state calculations on my water. But yeah, HFC SCF is good for a lot of systems, including the ones, some of the ones which I was showing you in the previous presentation from Harren's work. So next up, one can select their basis set. Again, if you have expertise in basis set, then great. If not, then the defaults work very well. And again, we're always very happy to help you. So just a quick nod to the advanced options at this stage. So if I would have chosen my Hartree-Fock orbitals, the advanced options is I can opt to use effective core potentials. This is effectively being able to speed the calculation up by using pre-calculated potentials for inner electrons. I can artificially impose charge. I can tell it what charge I want. I can tell it what multiplicity. I can change the symmetry group, and I can play with my memory requirements. If I were to have chosen MCSCF, you can also do things with the active space. So generally, we recommend an active space, I believe, of 10.5, but Sebastian can correct me on that one. 5.10, sorry, but Sebastian could correct me on that one. But yes, if you have expertise in active spaces, then great. The defaults work absolutely fine. So I wouldn't worry too much about that. But if that's something which you have expertise in, then by all means have a go, and we're always happy to help. The scientists are always happy to help. So if one clicks next after that, you can see some more options. So the first option is the R matrix sphere size. So the R matrix sphere, generally speaking, you want it to be large enough to encompass your molecule. So if your molecule is very large or is likely to have big diffuse electron clouds, then you can up your sphere size, maybe up to 14. But as our molecule is quite small, I'm going to keep it down at 10. So you just want to make sure your molecule is well encapsulated. And then you can pick your methodology of calculation. So if I were to have chosen Hartree-Fock orbitals, I would have the option of doing static exchange or static exchange plus polarization. These were the calculations, some of the calculations which you saw in the previous slides. Again, if you're interested in this, then I recommend reading the paper, which I'm going to link at the end, or talking to us directly about it, and the various merits of each of them. But since I chose my natural orbitals and I'm going to be looking at the excited states, I'm going to be using the close coupling methodology, which is the only methodology available. So next up, we've got our scattering energy grid. So you can choose your start energy, your end energy, and your energy increments. Of course, the bigger the energy grid is, then the more space it's going to use up on your computer, the more memory requirement, and also the longer the calculation is going to take. So sometimes if you want a quicker calculation or you want to use less memory, then you can specifically look over a certain region or use less increments. So yeah, that's worth considering. And then you've got some advanced options. So in the advanced options, one can change the total number of states, one can change the vertical excitation cutoff energy cutoff, sorry, and one can add extra virtual orbitals. So now we get to the final bit before the calculation. So this is where one selects what exactly they'd want. So if you've chosen your natural orbitals, then by default, well, not by default, but you will have it suggested that you do you calculate excited state cross sections, which is what we're going to be doing today, alongside the total elastic cross section and calculate the eigenphases. So you have some options for those three. So you can disable long range moments in the outer region. And then on top of this, we've got some more optional cross sections. So you can also use the binary encounter method to calculate ionization cross sections. And the options for this is you can either utilize Koopman's theory in order to calculate your ionization energy, or you can add in ionization energy either from experimental data or from literature which you may be in possession of. On top of this, you can also you calculate differential momentum transfer and rotational cross sections. So if you were to do that, you have some options. You can again modify your energy grid in order to make the calculation more focused, so that you don't need to use so much memory and also so it takes so much time. And you can either use calculated dipole moments, or you can put in dipole moments that you've calculated experimentally or that you've got from literature. You can calculate your vibrational excitation cross sections, as you saw in the previous work. Again, you can play with the energy grid for this. You can estimate dissociative attachment cross section. Now, for this, you must provide dissociation energy if you're to be doing this, but you can optionally define a vibrational frequency, and you can suggest certain fragments that you believe would form. So you can, suggest, say, H2 and O minus, and you can also give an electron affinity for that fragment if you have that. So these are all optional, but you must provide dissociation energy. And then finally, you can calculate higher energy inelastic electronic cross sections. So for this, you have some options. But again, it is whether you want to use the Koopman's ionization energy, or whether you are interested in providing experimental ionization energy, or getting your energy from literature. So for the purposes of this, we are going to calculate just the first three. And I'm going to click run. So in practice, this has taken me about 3 minutes or so, 3 to 4 minutes. And here we have some results. So we're going to have a quick look through our results here. So we can have a quick look at the total elastic cross section. So I'm just going to click view on this, and you can see you've got your total elastic cross sections here. It has both the elastic and the Born correction cross section. You can replot the axes as both linear and logarithmic. So I can move my x-axis to logarithmic scale. I can also use my y-axis to logarithmic scale, which can be very useful for seeing certain features such as these. And then you can save that as a PNG file. I'll show you in just a second how to save numerical data. So yep, that would save that as a PNG file. And you can close. So you can also view the rates associated with this. So here is the rate versus temperature, which is calculated. This is fitted data using Arrhenius fitting parameters, as you can see here. So these are your fitting parameters. Again, this can be plotted linearly and logarithmically in both X and Y scale. And you can save that as well as a PNG. So you can have a quick look at your eigenphases, which you can see here. So these are your eigenphases for calculation. As ever, you can change the scales on your X and Y axes to better view them to linear and logarithmic, should you see the edge. And again, you can save that as a PNG. So here are the excited states which we calculated. So you can see we've got our excited states here. So this is for various excited states with Born corrections as well. These can be plotted linearly and logarithmically, as you can see. And again, this can be saved as a PNG file. And then finally, we can have a quick look at the data sheet. So the data sheet is present here. So this will quickly take you through what was done in the calculation, what your molecule is, what's coordinates, its point group, the active space, the methodology, the basis set, and then you can see some other things like the molecular orbitals and their symmetries and their energies. It tells you what the dipole moment in that is, what the excited states are, some other factors about the calculation, and then you can see here that you have for those figures I just showed you, you can view raw data here for each of them and then click save to get the raw data. And you can do that for the rate data too. And again, for the excited states and the like. And then finally for this, we've got our reference, which you'd need to use the references, obviously. So what you can do is you can export the results of this directory. So if I were to do that, I could put it in, say, my Quantemol workspace here, into results. So I've got a lot of results here. And then I could select a file and save those. So I'm not going to save those ones exactly. But what I will do now is, if you have done that, if you were to click File, Open, and then Results, then you can click on a result set, click Open, and you will see your results sheet comes up again.
Is it possible to calculate electron impact cross-sections from excited state?
The answer is yes. It's not automatically played out on the screen. You have to go to the data files to find it, but the information is there. Indeed, I published a paper with a visitor to UCL earlier this year, on electron collisions with excited states of nitrogen, all entirely calculated with QuEC.